In this section, we're going to learn about the inverse trig functions. And if you don't remember what an inverse function is, now is the time to stop the video and go back and read that section, because this section is it's a little challenging for most people. Students tend to have trouble with it, so if part of understanding it will be understanding what an inverse function is. So there is a section in the textbook in the for I can't remember which chapter it is, chapter 2 or 3, on inverse functions, just a algebraic take on inverse functions, defining what that means, all of that. Go read that, review it, and then come back to this section, okay? Now I will say, just to remind you, just a quick reminder, recall that with a function you have a set of ordered pairs, right? You've got your input is x and your output is y, and it gives you an ordered pair x, y. And of course you have many of these ordered pairs, inputs and outputs, that make up the function. The inverse function takes all of those ordered pairs and switches the coordinates. So the y's become the x's and the x's become the y's. Whoops, you can't really see that. It's just chicken scratch, it's not that important, right? But we're going to switch the x's and the y's, remember that. But there's a lot more to it than that, so you should, if you don't have a good handle on that, you should go back and review. All right, well, I started my video before, so I have a lot of stuff written down here, but then I got interrupted and I decided I didn't get too far, so I'm just going to start over. And I'll just kind of walk you through what I already have written down here. So with the inverse function, the x's becoming the y's and the y's becoming the x's, we need to have that the function that we're starting with be a one-to-one function. If it's not one-to-one, right, you got x going to two different y's, for example, that's a function, but it's not one-to-one because when you've got one input going to two outputs. When you flip that around, you'll have two outputs going to one input, and then you won't have a function. So we need the function to be one-to-one, one input to one output. Well, none of the trig functions are one-to-one, right? Remember the horizontal line test. So I graphed the sine function here. So there's my one sine wave from 0 to 2 pi, but of course that repeats over and over. If you try to use a horizontal line test, this will fail in many places, in fact an infinite number of times, because the function's periodic. So you got like these two inputs are giving you the same output. So if you flip the x's and the y's, you'll have one output. Well, the one output becomes the one input, and that goes to two different outputs. The inputs become the outputs, and then you won't have a function. So we have to have the one-to-one requirement. So in order to make this work, we need to restrict the domain of the sine function. And so the green here is where I restricted the domain. We want to pick a part of the graph where you hit all of the numbers in the range. The range is from -1 to 1. So you don't want to just pick like 0 to pi, because then you only have the outputs from 0 to 1. You also want to make sure you pick an interval where you have a like all of those numbers are hit on a continuous interval, so you don't have to jump around. That would mean, jumping from one quadrant to another as you use the unit circle. And you want to make sure, like, this would be a bad choice because that's not even one-to-one, right? So the correct choice, well, it's correct just because it's by definition. So this is standard. It's obviously, there's other intervals where you can have the same, like the graph will look the same over here, right? But this is standard. We have to pick -pi/2 to pi/2. And so I re-graphed that right here, just this part of the graph from -pi/2 to pi/2. And so this little curve right here is just part of the sine function. It's y equals the sine of x on -pi/2 to pi/2. So we've restricted the domain. This is called the restricted sine function. So this function is one-to-one. Of course, it passes the horizontal line test. And since it's one-to-one, we can find its inverse. So now we're ready to define the inverse sine function. Well, if we were going to take the sine function, now this is the inverse sine, so this is on negative pi over 2 to pi over 2, right? Or what did I say? I meant to say this is the restricted sine function. So we're not taking the original, we're taking the restricted one. And then we interchange the x and the y. So this was the input, right? Now it's going to become the output. This was the output, now is the input. Well, the way it's written here, we want to isolate the output, so we want to isolate y. When we isolate y, we write y is sine inverse at x. So let's think about this some more, like what's happening here. So in this y equals the sine of x, remember this x is actually this arc length right here, or you can think about it as the angle in radian measure. That is not to be confused with this ordered pair x, y, where this x is, of course, the x coordinate, not the same as the length on the arc. So you might want to think of this as an angle just to help you remember what needs to come out once we switch the x's and the y's. So this was the arc length, or the angle is x. That becomes y. So when you isolate that, that's what y is. So notice in the definition, y, which used to be x, see this was our x came between negative pi over 2 and pi over 2. Now y is what is between negative pi over 2 and pi over 2. Likewise, in the original function, y goes from negative 1 to 1. Now that's x that goes from negative 1 to 1. So the inputs here are now the outputs, and the outputs from negative 1 to 1 are now the inputs. So we write y equals sine inverse at x, and that implies that the sine of y equals x. So when we say y is the sine inverse at x, we mean that y is the number or angle whose sine is x. In other words, if we take the sine of y, we should get x. Let me move that over a little. I'm going to zoom out because I kind of keep going out of the frame. All right, so it gets a little tricky. So because you have to reverse your thinking, okay? And that's hard to do until you get used to it. So here's a couple of examples. So you want, when we had y equals sine of x, you got used to those outputs for the special angles or the special numbers on the unit circle. So remember those outputs, the 1/2, the square root of 3 over 2, the 1, the 0, the square root of 2 over 2, those are the numbers that are going to go in. Now they don't have to be those numbers, but those are the ones we can find exact values for, okay? So when you see this, it's asking you what number has a sign that's equal to 1/2, or what angle has a sign that's equal to 1/2. Now when you do this, you have to choose your output, right? This is your output. You have to choose it between negative pi over 2 and pi over 2. So in other words, and if you think about the unit circle, negative pi over 2 is down here, negative pi over 2 is up here. You're choosing your answer, your angle, your number, if you will. Choose the number in quadrant 4 or quadrant 1. And the quadrant 4 number has to be a negative number between negative pi over 2 and 0. So if this is a positive, you choose from quadrant 1. If this is a negative, you choose from quadrant 4. So sine inverse of 1/2 means what number has a sign equal to 1/2? Well, that would be pi over 6, since sine of pi over 6 equals 1/2. That's all we're saying. Okay, so we're reversing the inputs and the outputs. When we give the what was the output is what we give first, and we find for the trig function. Again, this is the restricted trig function, so we're not going to say 5 pi over 6, even though the sine of 5 pi over 6 is 1/2. That is incorrect because that's not defined here. This is the definition. Y has to come between negative pi over 2 and pi over 2. Again, that's so that we have a function. We have to have just one answer. If there's more than one correct answer here, we don't have a function. So this is the only correct answer. And do not give, oops, I forgot my W. Do not give the angle measure in degrees. This has to be in radians, okay? I don't want to see 30 degrees here. All right, let's do B. Sine inverse of negative square root of 3 over 2. So that is negative, so it's got to be down here. And reference angle would be pi over 3, so it's negative pi over 3. Again, that's because the sine of negative pi over 3 is negative square root of 3 over 2. Yes, there's other numbers you could take the sine of and get negative square root of 3 over 2. But by definition, we have to pick the one in this interval. There's no other choice. See, this is the only correct answer, or we don't have a function. Okay, go to the next page. C. Well, this should have been. I should have had a carriage return. This should have been on the previous page. Maybe I'll do that. Just do that. Put it down here. C is sine inverse of negative 1. So this is down here, right? This is where the y coordinate is negative 1. So that would mean the output here is negative pi over 2. My negative and my equal sign are running together. And so the sine of negative pi over 2 is negative 1. All right, let's cross this off. Okay, once we kind of get the idea of what's going on with sine and sine inverse, cosine and cosine inverse, we'll develop this a little more quickly because it works very much the same. So let's start with the cosine function. Remember, that starts at 1 and ends at 1. Halfway in between is negative 1. We got pi over 2, 3 pi over 2. And of course, this cosine wave keeps repeating. So here's y equals the cosine of x. Notice if I choose negative pi over 2 to pi over 2, right, sorry, I'm getting ahead of myself. That's not 1-to-1, right? So we want to restrict it just like we did with sine. And if I restrict it like the sine function between negative pi over 2 and pi over 2, notice that does not give me a 1-to-1 function. And again, in the unit circle, cosine is positive in quadrants 4 and 1. So you wouldn't get all of the outputs there. You want to make sure you get negative outputs as well for y equals cosine x. So a better choice is to choose from 0 to pi. Notice then you get all the values from 1 to negative 1, right, for our outputs. So cosine, we're going to choose from 0 to pi. Or we restrict, and then in our inverse function, our outputs will go from 0 to pi. So our inputs here are 0 to pi. That means our outputs for inverse cosine will be 0 to pi. Well, let's graph that. Restricted cosine function. So y equals cosine x on 0 to pi is the restricted cosine function. And of course it is 1-to-1. And if it's 1 to 1, it's invertible. So just like with the sine function, we start, with our y equals cosine x instead of y equals sine x. We interchange x and y. X then equals cosine of y. So y is the number whose cosine is x. We just write y equals cosine inverse at x. So y equals the, sorry, I should put that down here. Y equals the number whose cosine, I don't know how, that's not the best grammar, but hopefully you get the idea. The number whose cosine is x. Right? The number, I should put y. So y is the number whose cosine is x. Again, that number, you might want to think of it as an angle. If that helps you, just to call it an angle instead of a number. So notice that y, the output now, has to come from 0 to pi. 0 to pi. That way you're getting here x, the x meaning the x coordinate, which is the value of the cosine function, is positive, and here it's negative. So we get all the values from, remember, cosine is 1 here, 0 here, negative 1 here. So all of the values from 1 to negative 1. That's what this graph represents, right? The x coordinates as we go from x equals 0 to x equals pi. It gets confusing because you use x in 2 different ways, right? I know that's a little confusing, right? X, y, cosine is the x coordinate, and then I say as x goes from 0 to pi, I'm talking about a different x. The x is the angle here, and this is the x coordinate. All right. So let's do some examples. So again, these were what we were used to being outputs. Now they're the inputs. Again, these are the ones we'll be able to get the special, these are the outputs for the special numbers or special angles. So they become the inputs here, and then our outputs will become those special angles. At least the reference number should be, the reference angle should be a special angle. So cosine inverse the square root of 2 over 2 is equal to pi over 4, because the cosine of pi over 4 is the square root of 2 over 2. Again, pick the number that falls in 0 to pi. Cosine of negative 1, well, cosine is negative 1 over here. The value of x that, or input here, I'm talking about the input that would give us this, that falls in 0 to pi, is pi. And that's actually y here, right? Cosine inverse of negative 1/2, that's got to be in quadrant 2. And this will be 2 pi over 3. You should recognize the reference angle is pi over 3, and then pick the value where y is between 0 and pi. All right, and now I realize I forgot to mention the arc sine and the arc cosine notation. I've been just using sine inverse and cosine inverse, but notice in the definition I said or y equals the arc sine of x. That is an interchangeable notation for the sine to the negative 1x. That of course means sine inverse of x, right? It's not actually an exponent, but that's interchangeable notation. Likewise, arc cosine of x is cosine inverse at x. So you should be familiar with both. For those of you going on to calculus, our textbook that we use at North Hennepin, the Stewart textbook, does use this notation sometimes, so make sure you're familiar with it. And that notation is coming from the idea that, like, when you find sine inverse of 1/2 is pi over 6, pi over 6 is actually the length of the arc. And that's why it's called arc sine. Okay, the pi over 6, remember, that's the arc length. All right, well, let's do tangent inverse. And that one, I don't know why I have that one graphed, and the other ones I don't have graphed. But here's our tangent inverse function, or not inverse, just our tangent function. Y equals tangent of x. And of course that is not 1-to-1. So it's not invertible. Well, there's a real natural choice, isn't there? Because you can see we have continuous curves in between the asymptotes. So we're going to pick between negative pi over 2 and pi over 2. So this is almost the same interval that we have for our restricted sine function. I say almost because the sine function includes negative pi over 2, but the tangent function does not, because the function is not defined at the asymptotes. So y equals tangent of x on open interval negative pi over 2 to pi over 2 is the restricted tangent function, which is a 1-to-1 function. Since it's 1-to-1, we can find its inverse. Right? We just start with y equals tangent of x, and then interchange x and y. So x equals the tangent of y means y is the number whose tangent equals x. So this implies y equals tangent inverse of x. So again, that notation, that's not an exponent or anything, it's just representing this statement here. This notation represents this, just gives us y isolated. So when we have an input x here, now notice those were originally the y's, right? These numbers, the inputs, can be any real number because the range of the tangent function is all real numbers. That becomes the domain of the tangent inverse function. So notice in the definition, y equals tangent inverse of x, x can be any real number, negative infinity to infinity. The output y has to come between negative pi over 2 and pi over 2. All right. So when we talk about the tangent inverse of the square root of 3 over 3, you're talking about, again on the unit circle, picking your answer from negative pi over 2 to pi over 2. Of course, this is negative, tangent is negative in quadrant 4 and positive in quadrant 1. Since this is positive, you're picking from quadrant 1, and this will be pi over 6. So you should have that memorized. Tangent of pi over 6 is square root of 3 over 3. So then you should be able to work backwards from that. This is true because the tangent of pi over 6 is the square root of 3 over 3. Tangent inverse of negative 1, this has got to come from quadrant 4. Tangent is negative 1 at negative pi over 4. So don't pick 7 pi over 4. 7 pi over 4 is wrong. It's negative pi over 4, not 7 pi over 4. Yes, tangent of 7 pi over 4 is the same number, but that's a different output. We can only have one output, and by definition it has to be the negative number or angle from negative pi over 2 to 0. It takes some getting used to. After we finish this example here, you should pause the video and do some more examples on your own. Make sure that you understand how to find inputs and outputs. Just look some up in the textbook and practice. Okay, now when we go on to C, tangent inverse of 5. 5 is not an output for one of the special values. So this is not one that we can find exactly, right? So that's why I said if possible, otherwise approximate using a calculator. We need a calculator for this one. The outputs have to be in radians, so you make sure you have this in radians. And I gotta check mine. Mine's not in radians, so I need to change it. Turn this light off. Okay, quit. So that here's your usual sine, cosine, tangent. Now, you might not have, on the test you can't use this calculator. Again, I always forget to bring my other calculator home. But it's just like this on the TI-30s. The inverse sine, inverse cosine, and inverse tangent are right on using the second function, the same keys on the calculator. So we want to use tangent inverse. So that's not 1 over tangent. That means what number has a tangent that's equal to 5. So tangent inverse of 5 is approximately let's just approximate to 3 places, 1.373. Okay, so that means the tangent of this is the arc length, remember. We're talking about pi over 2 is approximately 1.57. 1.37 is maybe right here, and then we're talking, so that's this. This 5 then is the ratio of the y-coordinate to the x-coordinate. And remember, as we get closer and closer here, that ratio gets bigger and bigger and bigger. All right, sine inverse of 5. So what number has a sine of 5? Well, the outputs for sine are all from -1 to 1. So we can never get a number that has a sine that's equal to 5. So this is not defined. And if you plug that in your calculator, we'll just do it. You get an error because that's not in the domain. Yeah, we'll take not defined out of there. We should just say 5 is not in the domain. Okay, cosine inverse of 0.75. That is smaller than 1, so this is defined. What this is saying is, okay, the arc length is 0.75. No, sorry, that's the x-coordinate is 0.75. What's the arc length, basically? Or what number has a cosine that's equal to 0.75? So that's going to be, like if I were going to estimate, here's where x is 1. It's going to be somewhere here. That's 3/4 of the way to 1. All right, but we'll use a calculator to approximate. Oops. Cosine inverse of 0.75. About 0.723. 0.723. So again, that's this arc length here. Then the output is the arc length. All right, so this is a good time to take a break and you go and practice some of these. Not necessarily the ones with the calculator, but especially the ones with the special values, because on the test, you'll have, these will be on the part of the test that you cannot use a calculator, right? Now these ones might show up on the test, the part with the calculator, but these you should be able to find exactly without a calculator, so you want to practice some of those. Get used to that, reversing the inputs and the outputs. All right, I'm going to take a break here.